The following presentation was recorded at the 2025 Southeast Linuxfest in Charlotte, North Carolina. It is licensed under a Creative Commons license. For more information on the Southeast Linuxfest, visit www.southeastlinuxfest.org. Come join us next June.
Yay! Starting time. Okay. My talk is the two greatest lost programming languages. Of course, some qualification here. I think they're great. Other people may not. So, one qualification. Lost, they're not actually lost. I mean, I know about them. A lot of other people know about them. But chances are, most people in the computing world today have never heard of these languages. Subtitle, How Two Languages Older Than Me Blew My Mind. Second subtitle, How I Accidentally Inherited a Fourth Project. Oh, my name is Dan Good, for what it's worth. I work at Microsoft. Been working with Unix since 1990. So these two men, one of them is Chuck Moore, born in 1938, and Ken Iverson, born in 1920 and deceased 2004. And these are some real heroes in the computing industry. I don't know that I'll say too much about them until I get to the timeline slide. So we'll just keep going. So this is FreeForth 2. It's my project. This is the one I sort of inherited. The first time I encountered Forth was in the 1990s. Sun's Open Boot Prom was programmable in Forth, and two of my mentors told me, yeah, this is really weird, and that's about all I knew about it for a very long time. Much later, a guy out there wrote something called Jones Forth, which was his attempt to make a Forth environment from scratch and do it in a way that he could educate other people. And I thought that was pretty cool. But it actually raised a fair bit of controversy because there were some gatekeepers in the Forth community who thought that Jones Forth wasn't really doing it just right. So there were other efforts like UForth by Albert Vanderhorst, which tried to show, a much more, tried to show a better Forth implementation. So when I was looking at these, I'm like, you know what? I don't actually want a pedagogical Forth. I want a Forth that's real and does real work and tells me something, because I don't want to learn a toy. I want to learn something real. So when I went looking around for the small Forths that basically compiled to machine language, the small Forths that were like compilers and assemblers, we'll say it that way. One of the ones I came across was by Christophe Lavarine. This was in early 2016. And I thought it was cool because it did so many things that I just couldn't understand. And I like a puzzle. So, I spent a lot of time trying to figure out how this did what it did. And in the process, I decided there were some things I really wish it did that it didn't do. So I decided to add some of those things. And some of those things are like turnkey support. And that's where you take an interactive environment, drop its core, and turn that into an executable you can use later. And some other things that I thought it should have, like mmap. Everybody wants mmap in all of their programming environments, right? That's very nice. So I made these changes, and I thought, one day, this Mr. Lavarine and we're going to have a conversation. One day he's going to stumble across my changes, and he's either going to love them or hate them. And I look forward to that day and having that conversation with Christophe Lavarine. And only many years later did I discover that he had actually died in 2010, a full 6 years before I ever even encountered his project. And once I understood that he was no longer with us, and I was probably the only one keeping his work alive, I decided to kind of focus the effort to bring his writings forward onto a platform, GitHub, where they would be more easily accessed and things like that. So now the project has become more keeping this alive and trying to do service to someone who gave so much away for free. So that's FreeForth 2. All right, so here are some early Forth milestones. We'll try. I should keep an eye on the clock because I haven't actually timed this. So Moore was an undergrad at MIT, and he worked at a bunch of interesting places, like the Smithsonian Astrophysical Observatory. And there he wrote an interpreter and reading from punched cards, right? Because this is before there are even really useful teletype terminals. Later at Mohasco, he names his language Forth, and he does this because he's working on an IBM 1130, and the file system on the 1130 doesn't actually allow more than 5 characters in a file name. So it was supposed to be Forth with a U, but he dropped the U so it'd fit. In 1970, he publishes his first paper on Forth. In 1971, Elizabeth Rather becomes the second Forth programmer while they're both at the National Radio Astronomy Observatory. In 73, they formed Forth Incorporated and proceeded to do lots of work, commercial work, and be basically a commercial success. The first preliminary standard was released in 1977, Forth 77. And in those late 70s, the Forth Interest Group started, and they published FigForth, which was their implementation of Forth in the public domain for microprocessors. And once they did that, a whole colony of new implementations sprang forth for all of the different new microprocessors that were coming out at the time. And then later we have one of the most popular introductory texts to Forth, lit by Leo Brody, starting Forth in 81. And in 94, we finally get a Forth standard that becomes an international standard. So Forth probably peaked in the 80s. This is the cover of a book from Forth on the Atari, and the book itself is really dry. So this cover is just, I just saw it and I thought, oh, I have to show this. Now, for what it's worth, I'm the one who made it G-rated. If you want to see the much more evocative cover, you can Google that title. So I have just a little snippet to show you Forth in the 80s. We'll pop over to, this is Elizabeth Rather on television in the 80s talking about Forth.
Joining us now is Elizabeth Rather. Elizabeth is president of Forth Incorporated of Hermosa Beach, California. Elizabeth, tell us about Forth. What makes that a unique programming language?
It's unique in 2 respects. First, it is the only language that I'm aware of that was designed for from first principles to run in a small computer, doing interactive software development for real-time applications. The second area that it's unique relates to Gary's remark early in the program when he mentioned the 3 levels of programming, and Forth incorporates all of them. You can work right down at the machine code level when you need to. You can do system programming in Forth. In fact, the operating system that we're running on here was all written in Forth. And you can do very high-level kinds of things, very high-level application-oriented programming. For example, we have here a graphics program.
All right, that's enough of that. Thank you, Elizabeth Rather. Wow, I dare not speculate. Okay, let's go back into the slides. Okay, the Harris RTX 2010. So in the 80s, Chuck Moore became very interested in getting Forth down at the hardware level. So he designed a chip called the NC 4016, and he formed a different company to sell that chip, work on and sell that chip. And this was a 16-bit dual stack machine running Forth directly. Now, Harris Semiconductor licensed this design, and they added a few features like some interrupt handlers and some on-cache memory and some timers and some things like that. And they marketed it for low latency real-time uses. Oh, they also radiation hardened it. So what were they targeting? They were targeting spacecraft. Now, before I get to, and that brings us to fourth in space. So before I talk about this particular spacecraft, let me just, oh yeah, I have to exit this thing. Go. Wow, sorry. Here we are. So
Loaded.
no,
And I
no,
have
no,
a
no, no,
list
no, that's
of
enough.
a large
Stop.
number.
Apologize. So fourth in space. This is a table of missions that used fourth in space, and it's not actually completely up to date, but it's just really long, I guess is what I'm trying to say. And about half of these entries credit the Harris RTX 2000. So now let me go back to, and this went too far, fourth in space. So this is the European Space Agency's mission, their Rosetta mission, which had the Philae lander. I'm probably massacring that name. But these two spacecraft, I'm just going to read their blurb, carried 20 scientific instruments to make a detailed study of the comet 67P Churyumov-Gerasimenko for 2 years as it orbited around our sun. In August 2014, Rosetta became the first spacecraft to orbit a comet when it joined the comet on its journey around the sun. On November 12, 2014, Rosetta scored another historic first when its Philae probe lander landed on the surface of the comet and began sending back images. There's actually more to this story because it kind of bounced on the comet a few times and it did not land exactly as planned. So the mission ended successfully when they crashed Rosetta into the comet on September 30th, 2016. Intentionally crashed Rosetta into the comet. So the lander is powered by two 8 megahertz Harris RTX 2010s. That's the fourth processor. And it also, so these are used by the command and data management system to control all aspects of the lander. And 8 of the scientific instruments are also powered by RTX 2010s, making 10 total. So this is fourth in space on a critical mission in 2014. So not lost, amazingly, right? Let's keep going. Okay, so demo time. Mr. Laverine included a demo in his fourth. And it's just called, it's just the Towers of Hanoi, right? So that's not super impressive, but it's fun and I like it. And it's done. So what's probably more interesting is what that looks like. So here is your first look at some fourth code. Now, all of this first part is just the help text that it shows, but this is embedded inside the text in an interesting way. I'm not going to try and read through all of this, but I am just going to show you maybe this much. Maybe I think I have it on the slide. I'll go back to the slide. Because I kind of want you to have just an impression of it, and then I'll show you a short bit. So this is 30 lines, and that's all the demo was. And doing something in 30 lines, I'm a C programmer, and you know, we can write hello world in 30 lines. But so I just enjoyed this, and I thought I'd share that with you. Now, this is a little bit of code I wrote. You know, I said earlier, every implementation should have mmap. So this is cat. This is cat written in the Free Fourth 2 dialect of fourth. And I'll walk through this just quickly. So we have main, and that's where execution starts. And very simply, we're putting a 0 on the stack. We're taking the count of arguments, putting that on the stack. We're decrementing it once just to make up for the fact that that argc includes the name of the program as its first argument. And then we're doing a loop, so that times repeat is going to loop that many times. We index 1, we're duplicating that onto the stack. We're calling argv. That replaces the top of the stack with a pointer and a length for that first argument from the command line. And then we call the word cat. So cat is the function defined one line above. So what it does is it calls mmapr using the struct at m, and then it asks if that worked. So mmapr is going to open the file, it's going to mmap it, and then it's going to either return a pointer or a negative error number. So this is the raw system call. So it's not like you get a -1 if it fails. You actually get the error number that you would normally find in ERRNO, and you get it as a negative. But it's kind of hard to tell when you're getting back a pointer and when you're getting back a negative error number, because a pointer can look like a negative number. It's just that the top bit is high, and that's how we tell that it's negative. So this OK function actually has to do some fun. It takes that return value, and then it takes FF, so all bits on in the lower byte, and it ORs those two together. So when you OR FF with that, with any number in between -1 and -256, what you get back is -1. And that's because the representation of -1 is all bits on. So if it were -2, the lowest bit would be a 0. But when we OR it with FF, it all goes back to -1. So this is, and then we add 1. When we add 1, we're actually setting the 0 flag on the CPU. And in this particular implementation of Forth, the conditionals work with respect to the CPU flags. So that 0 equals says the next conditional is going to use the 0 flag on the CPU register. This is something that's kind of peculiar to FreeForth. In most Forths, you would just use a 0 or 1 on the stack to say true or false. But this one's a little different, and it's got to have its own way of doing things. So if we do have an error number, we're just going to use str_error from the C library to print that out. We have good interop with C for what it's worth. And then this is the part that kind of blew my mind. Then it does an rdrop. What is rdrop? Rdrop takes the top element from the return stack and drops it. Now, why would any function mess with the addresses on the return stack? Well, it does that so that we don't actually have to exit out of the cat function ourselves. By doing the rdrop in OK, the cat function is ended when we return, and we basically return right back to the loop in the top main function. And that is kind of mind-blowing, because no other language lets you have that much control of what happens with your CPU. Now, I take that back, because of course assembly does. But beyond assembly, no high-level language lets you really work with your CPU and really get into the nooks and crannies. So this is the first time a language older than me blew my mind. All right, let's go on. Forth today. So Forth, like I said, it's not truly lost. There are high-quality implementations like gforth. The Silicon Valley Forth Interest Group still meets monthly online, and you can find recordings of all of their recent sessions on YouTube. So now, I will grant that they are a very advanced in age community, but don't hold that against them. There are a few new people who show up now and then. So emulators also exist for many retro Forths. So the Jupiter Ace was one of these microcomputers that was released with Forth embedded on it, compared to, like, say, your VIC-20 and your Commodore 64, which had BASIC embedded on them. This had Forth embedded on it. And you can now pull up on your iPad an emulator that lets you get the look and feel and actually have the manual there. And well, here, why don't I show you a? I think I have that in my browser right now. So we'll pop over to the browser. What do we? So Gforth, that's Gforth's page, and if you're interested, they support a bunch of systems. You know, even Android. So that's cool. And here's that that app I was talking about. So it even gives you an image to mimic what you would have seen if you were sitting in front of an actual Jupyter Ace. And I love the wide characters. You know, I don't know how many people remember, but early microcomputers, they had 40 characters wide screen, and that takes me back to see a 40 character wide screen. And the only other one I was going to mention, just for the novelty sake of it, is Collapse OS. This is a whole new Forth OS, written in Forth because he wants it to be easily understandable and easily maintainable. And his idea is that the end of civilization is coming. But after civilization ends, for some period of time after civilization ends, we will still have a bunch of working computers around that are going to be suffering bit rot. So in order to be able to continue to use the computers we have lying around, he's making this super simple to maintain, easy to use Forth operating system available. Okay. So this is Collapse OS, and that's all I'm going to say about that, because I really hope civilization isn't ending anytime soon. All right, so that was Forth today. Let's go on to the next language. All right, I hope we're about halfway through. So the next, where's the button? Okay, the next language is APL. This is Iverson's language. And I'm just gonna, I shouldn't have full screen this just when I want to go right back to the browser. I'm going to show you a little clip from 1975.
The use of row here in its monadic form to find the dimensions of the matrix M. It's a 3-row, 3-column matrix. Now, we often need to carry out matrix multiplication. Now, ordinary matrix multiplication is not achieved by entering M times N. This simply gives one the element by element product of those two matrices. We obtain matrix multiplication by entering M
Roll the paper up.
plus dot times N. Why? Well, very simply.
Get out your
Look at
Bic.
this operator here, plus dot times. This means that I take the element by element product of rows of M with columns of N, and then I take the sum reduction over those products.
All right, that's enough of that, but that gives you a flavor for what it was like in 1975. Now he's working on one of these terminals with the Selectric ball that has the APL font built onto it, and that was the only way you could do APL at the time. It doesn't say what computer he's using, but it's probably an IBM 1130 or a 360. And I think what I just love about this is, you know, this was state of the art. Paper, working on paper, interacting with the computer in real time, interactively. That's just that word, interactive. We take it so for granted these days. But not long before this, people were using punch cards, and people were still using punch cards in the 70s. So it was, there you go. So that's kind of dramatic. So let's go back to the slides. Okay, now we have a timeline for APL. So from 1955 to 1960, Iverson's teaching at Harvard. He's working with Howard Aiken and Fred Brooks. And, you know, if you're into computer history, these are some really big names. You might know Fred Brooks from the Mythical Man Month. You might know Howard Aiken because of the Mark I computer at Harvard, which was important in World War II. So during his time at Harvard, Iverson is frustrated by the inability of mathematical notation to express what he wants to express in unambiguous ways. So he starts working on an improved form of the notation, which becomes known as Iverson notation. So in 1960, Iverson joins IBM Research, and then he publishes a book called A Programming Language, and that describes his notation. And if you ever leaf through it, it's a pretty dense book. The APL notation was actually used to describe the IBM, I want to say 1130, as in engineering documents. So the notation itself was used to describe what each register would do and how they would interact, and it's kind of mind-boggling. But what's also mind-boggling to me is that he wrote this book, a programming language, for a theoretical language that had no implementation. So it would be 4 years later when the first implementation that actually let you type APL would exist, and that was the APL 360, completed for the IBM System 360 mainframe in 1966. Now, this was used within IBM, and it was later released in public in 1968, which means that this next one, 1968, APL 1130, released for the brand new IBM 1130 mini computer, was actually the first publicly usable APL. It was the first time anybody outside of IBM could get their hands on APL. And the one for the 360 was released shortly after. Now, so this was a big deal, frankly. In 1979, Iverson receives the Turing Award, and that's a pretty prestigious award. His speech that he gave when he received the award is pretty famous, and he describes APL, and he calls it a tool for thought. And so now, kind of one of the highest compliments that can be given to an array language is saying that it is a good tool for thought. So Dialog APL is one of the big commercial implementations of APL that is still going strong today, and it started in 1983. Now, Jay, in 1990, so 1990, which is 30 some odd years after Iverson makes APL, he decides that he's going to do a new array language with all of the good ideas and fixing all of the mistakes. And that language is J. So when I first started looking at which language I should try and pick up, I decided, well, if Iverson decided this one was better, I should go with this one. Now that choice is actually highly well, there are religious wars. We'll just say that. K, which was Arthur Whitney's language, so Arthur Whitney was a student of Iverson, and he made his language K. And K later became Q, and is probably the only time a programming language was sold for $100 million. Q is part of, is at the core of KX Systems, which is a very big player in the financial world. So you might have heard the word quant before. So a quant is basically a programmer, most likely working in something like Q, who is managing to just reap huge amounts of money out of the fractions of pennies that move through markets. So to be a quant is to be, basically a big brain in the finance world and using something like one of these array languages. I am not one, for what it's worth. I barely understand anything they do. I just thought I'd throw that in there. So when we talk about Iverson languages, we're basically talking about a family of languages. So APL was the first, and of course then there was a J that I mentioned, K from Arthur Whitney, which led to Q, and then I is kind of out there. Dialogue APL is still quite strong. These last three are recent languages, BQN, CAP, and WIWA. So we'll have more to say about them in a minute. Now, what captured my imagination about J? Why did I look at it and go, what blew my mind? This is what blew my mind. These 4 symbols at the bottom, or 3 if you want to think about the sum as a digraph. These 3 symbols are the entirety of a program in J to do an average. And you wonder, how is that even possible? Well, it's possible because J has this notion of a fork. It also has a hook, but I'm only going to talk about the fork. In a fork, and what makes it a fork is having these 3 verbs, and they call functions verbs. So these 3 verbs just pressed together. What makes it a fork, or how a fork behaves, is that the argument to this program is given to the first function, and it's also given to the end function. So each function gets to work on its own copy of the argument, and the results of each function are then combined, or rather are then given as 2 arguments to the middle function. So if you think about that, well, then it kind of makes sense. The average is just the sum of the numbers and the count of the numbers divided. So it's really straightforward, except it's so terse. It's kind of mind-blowing. For what it's worth, this notion of a fork is actually something called a combinator. And there are many different kinds of combinators, but that's a whole nother talk, so we'll leave that alone. So now we're going to get close to demo territory here. So Conway's game of life. Does everybody know what Conway's game of life is? Okay. Very quickly, cellular automata. Some cells are on, some cells are off. The next generation lives or dies based on how many neighbors any given cell has. This is Life in APL by John Scholes. It's kind of famous. It's also impenetrable until you've learned a fair bit of APL. So I'm not going to try and walk through this for you, but I am going to show you quickly John Scholes talking his way through this. There. We'll go back over here. Let me make sure I have this at double speed, because
Here is a vector of the first 9 natural numbers. The 3 by 3 reshape gives us a 3-row, 3-column matrix. Which of the items of the matrix are members of this vector, 1 for yes, 0 for no, and we'll call this Boolean matrix R. We can embed R in a slightly larger matrix, the 5 by 7 take of R, which pads below and on the right with zeros, and we can center our original within this by doing the -2 rotate around a vertical axis, and the -1 rotate around a horizontal axis. And we'll call this larger matrix uppercase R. Here is a vector of 3 matrices, and we can see this more clearly if we copy in a library function also written in APL, which draws boxes around subarrays. The 1 by 0 by -1 rotate each distributes the rotation between corresponding items in the left and right argument vectors. So we see our original 0 rotated in the center with a 1 and a -1 rotation on either side. And we can simplify this slightly by having just one copy of R, which is enclosed to form a rank 0 array, which is distributed to each item in the left argument vector. So we get the same result. Next, we'll do the 1 by 0 by -1 outer product column rotation. And outer product takes each item of the left argument and distributes a function between it and each item of the right argument. So we get a table or a matrix, in this case a 3 by 3 matrix, with our original in the center surrounded by all possible.
I'm going to skip forward.
And if we do a column sum of the 3 by 3 matrix, we get a function that is applied by the fixed point operation. And changes in this global variable will be reflected in the edit window, so we should see it working. Before we do so, I'll make just 2 small refinements. Firstly, I'm not interested in the Boolean result, which is a fixed vector 2. operators that take our life function as an operand, and the operators produce life on other manifolds, such as an infinite plane or a Klein bottle or a Möbius band. And if you Google for dialog creatures, you'll see a web page which shows how to do this. If you're using Internet Explorer as your browser, then the APL font will download it automatically.
Okay, so that is Life in APL by John Scholes, and it's kind of famous. You know, it's only 7.5 minutes long, and it has inspired quite a few people to learn APL. It inspired me to not learn it, but to try and to try and do a version of this in J, because J was the one I'd been studying. Now J uses ASCII characters instead of these interesting symbols. So what does that look like in J? Let's just go to the next slide. So this is my version in J, and I'll walk you through it in much less than 7 minutes. So let's go over here. So here, well, that's hard to see, isn't it? Let's go over here and okay. Let's see. That's better. Okay, so here I can have a 5x5 matrix of the number 2. The $sign stands for reshape, but we won't dwell on that. I can use this question mark to give me a random number lower than the number in each cell. So this gives me a random matrix of 0s and 1s that has the shape 5x5. This is just an init function which does the same thing, but it uses an argument. And the way it's using this argument is that bracket. That bracket actually stands for the right-hand argument. And this is written in tacit style. So all of the arguments are expressed implicitly rather than being given names. So that's just an example of doing it that way. Now here, this next one is kind of a clever way of just making this set of constants. These are a set of translations I want to do. So I want to take the values in that matrix and I want to shift them one to the left and up, one up, and in each of the 9 different directions. And that's what that represents. And if I try and do a John Scholes and draw boxes around what that looks like, it looks like this. Now, the interesting thing about this is that if you take each of those different shifts and you sum them together, you sum through each cell, so the 0th cell in the first box with the 0th cell in the second box and so on and so forth, you get these totals. These totals actually can tell you what's going to be alive in the next generation, because anything with a 3 or a 4 here is going to live in the next generation, and everything else is going to die. So it's actually a really simple way to get the next generation, is to just do this sum. Now, since we're looking for 3s and 4s, I just subtract the original matrix from this sum, and that gives me, so now I have two matrices, but the 4s have been decremented by 1, so now I only have to look for 3s. And that's what happens. All right, so that's just, where does that happen? That happens here. Okay, so I maybe skipped a little bit here in that, all right, so here f is a function that's doing these rotations. You can see the s's there. That bar dot is that translation function. That +/ is the sum function. So all of these functions are just placed side by side, and the arguments are flowing through them in an implicit fashion, so that I can just say f on m and get that result. And then if I wanted to subtract the original matrix from that, that's just f on m minus m. And then I can make G, which just is I forget what G does. All right, we'll just keep going. No. I'm running low on time anyway. All right. So that's the final output. Basically, you see there's that 3 equals in there, and that's what's finally going to give us the next generation. So let me show you this actually running. Bup. So now, John Scholes had some nice stuff to make his show up. I needed to add some extra code to make mine show up. So that's what the stuff below the first 4 lines is. So that just copied it from the editor into here, and now I'll just say there. And so this is life in J. And that's the demo. So yay, demos worked this time. That's fun. Now I only have 1 or 2 more slides, I think. I hope. So let's get back to this and try to finish on time. J by me. Okay, so this is just a visual diagram of the Iverson languages and where they live in the larger world of array languages. And these Iverson languages, some of them are new, some of them are very old, but they have had incredible influence on all of these other languages. You might have heard of some of these like NumPy and Julia. Those are pretty popular these days. So let's just go into some resources. If you're interested, now this is particularly for the Iversonian languages. If you're interested in any of, in finding out more, the APL Wiki is a great place to find out about any of these languages. That's at aplwiki.com. The Arraycast is a really good podcast that's well over 100 episodes now that is specifically about array programming. You can interact with Dialog online, also with J online, also with BQN online, also with Wiwa online. So I haven't really said anything about BQN and Wiwa other than their descendants. But I will just pop over here. Oh, and I did mean to mention that the Dialog user conferences are still going strong. And if you want to see videos of all of their past user meetings, you can find all of those on YouTube. So this is the Try APL online. Oops. And here's BQN. And BQN is kind of interesting because he chose a new set of symbols, and they're pretty wild looking. And then I will say just a word or two about Wiwa. So Wiwa is probably the newest, and it's probably the weirdest, in that Wiwa is an array language, but it works on a stack paradigm. So we were talking about Forth before, and I guess I didn't really dwell on it, but Forth is a stack-based language. All of the arguments go onto the stack. You push a 2 onto the stack, push a 3 onto the stack, do plus, it takes the top 2 numbers off the stack, adds them, and puts the result back on the stack. So that's what a stack is like, and that's why you don't have to have a lot of memory allocation or a lot of parameters or things like that. In the case of Wiwa, it adopts this same concept of a stack. So here with Wiwa, you can actually get some of the nice flavors from Forth and some of the nice flavors from APL and have them all rolled into one. And this is a growing language. So 2 greatest languages, not really lost, great only by my opinion, but there you have it, and I'll stop there. Yeah. If anybody has any questions, I might be able to answer them, but I might not. But you're welcome to try. Here we have one. Let's see, turn it on.
This one was really simple. I was just asking what that array language podcast was called again.
Arraycast.
Arraycast.
Yes. And actually, several of the diagrams that I used came from Connor Hoekstra, who's the host of Arraycast. So I did give him credit, but I didn't have to make that diagram myself. Any more questions?
I will say my only interaction with APL was when I was working at Union Carbide back in the early 80s as a summer intern kind of thing. And they had a portable terminal there that had APL key, all the symbols on it. And I was just fascinated by that thing, but I never actually got to use it.
It's not too late. It's still out there just waiting for you. All right. Thank you, everyone.
Thank you.